We present a system for Oblivious coopetitive analytics using hardware enclaves. This is joint work with colleagues at the UC Berkeley RISE Lab. SQL analytics is essential to modern enterprises, which use data warehouses and distributed data flow engines to extract value from their data. These systems focus on data owned by a single organization, but many valuable datasets span multiple competing parties that cannot share data with each other. For example, suppose a bank wants to assess the system-wide risk from subprime loans. The best assessment requires competing banks to cooperate to answer this query. But the inputs to the query are sensitive customer and loan information. Sharing them is infeasible due to security concerns. Even if they shared the data using encryption, it would be vulnerable to two kinds of attackers. First, a network attacker may observe the network traffic patterns and infer sensitive information, such as the number of loans a particular bank has made. Second, one or more of the banks themselves may inspect or tamper with the computation as it runs within their premises to gain sensitive information about a competitor or to produce inconsistent results. A system for coopetitive analytics should be secure against both of these attackers. Prior work in coopetitive analytics uses one of two approaches. First, systems based on cryptography are either limited to a subset of queries or incur prohibitive overhead. The second approach is to use hardware enclaves. Hardware enclaves enable trusted code to run in an isolated environment where even the OS and hypervisor cannot tamper with its execution or access its data. Hardware enclaves are more promising for coopetitive analytics, but they suffer from side channels that allow an attacker to observe their memory access patterns. Observing memory access patterns can allow an attacker to infer secret information. Oblivious algorithms hide access patterns by making accesses according to a predefined schedule, but this comes at a performance cost. Prior systems that used hardware enclaves were either not oblivious or were designed for the single-party setting rather than the coopetitive setting. If applied to the coopetitive setting, they either require maintaining a remote copy of all data or require shuffling large volumes of data across the wide area. We propose a system called OCQ that's designed for Oblivious coopetitive analytics. It supports general SQL queries with good performance, and it protects against both network and malicious party attackers, assuming the security of the hardware enclave model. To use OCQ, parties first agree on a fixed set of queries and take a snapshot of their input data. They each run a replica of the OCQ planner, which generates a federated query plan that will protect all sensitive data. Each operator within the query plan executes in the enclaves of one or more parties and uses Oblivious algorithms when necessary to hide access patterns. The result is shared with all parties. Its integrity relative to the approved snapshot of the input data is guaranteed. In designing OCQ, we encountered three challenges. First, how to efficiently combine data of mixed sensitivity. Second, how to efficiently hide the cardinality of sensitive data, not just its contents. Third, how to efficiently execute Oblivious queries in the wide area. We evaluated OCQ on a variety of synthetic benchmarks. We used 5 geographically distributed parties and table sizes of up to 10 gigabytes. We compared OCQ against prior work. Here, lower is better, and this is a log scale. On the right, SMCQL and djoin use cryptography. OCQ is orders of magnitude faster because it uses hardware enclaves. On the left, opaque uses hardware enclaves and is designed for the single-party setting. OCQ is up to 10 times faster than outsourcing computation to opaque because opaque has to use expensive Oblivious algorithms for all operations on sensitive data, while OCQ can execute some operators in plain text. In summary, OCQ is an efficient general framework for Oblivious coopetitive analytics. Thanks for listening.